we will share our previous work on the OL2020 competition. Combining our daily work, we focus on Task 1, cross-channel LID, and Task 3, noisy LID. Consider the time cost. We only submit the final results of Task 1 and Task 3. We will describe the 3 steps. The first part is data preparation. The second part is our systems. And the last part is the results. The first part is the data preparation part. Task 1 is cross-channel language identification, identifying 6 languages, which are Cantonese, Indonesian, Japanese, Russian, Korean, Vietnamese. We use former competition training dataset and testing dataset. The training set used in Task 1 was named AP20 Task 1 Train, which only included the 6 target language. We first adopted the data augmentation, including speech perturbation. We apply a speed factor 0.8, 0.9, 1.1, and 1.2 to slow down or speed up the original recording. 4 augmented copies of the original recording were added to the original dataset. We also convert the format of audio data from WAV into MP3 and then convert it back to WAV because we found last year cross-channel language task had some testing data which were converted from MP3 formats as the below spectrum photo shows. For Task 3, as for Russian, Korean, and Japanese, there are 2 recording sessions for each speaker. The first session was recorded in a quiet environment, and the second was recorded in a noisy environment. We also adapt the speed perturbation to do the data augmentation for Task 3, just as the Task 1. Because of the mismatch of the training and the testing data, there are 2 ways to alleviate the mismatch: denoise or add noise. First, we try to denoise the training data, which are recorded on noisy environments. We use the WPE algorithm to do reverberation, and the linear Wiener filter is used to reduce the noise. Unfortunately, the denoise system is not performance as well as we expected. Finally, we use energy-based voice noise from the noisy training and randomly select those noise fitting to the training dataset. This is the data preparation part of Task 1 and Task 3. Next is the model part. Our system is based on end-to-end free. The 2 tasks basically use the same system. Only difference is data preparation and output node dimension. Because the task we select a closed set job, it is very clear that the environment
请你静音。
这个岗位责任这个盘子是按照就是干货，就是你在这个岗位上应该做哪些事，比如教学科研就这么个意思。
Okay, let's go ahead.
We will continue. Use end-to-end framework for the co-set job for our system. We named the first subsystem non-local GRU attention. The input of the network is 40-dimensional F-band filters. Frequency voice active detection were used to filter out non-speech frames. We're using the KLD to extract F-band through the VAD. First, we adapted ResNet framework by adding non-local block and change the last few stages of the ResNet into GRU. The feature was sent to a ResNet block and then sent to a non-local block and finally sent to the GRU block. The non-local block is a structure which can capture long-range dependency. However, because of the temporal information will be lost because of the last stage of ResNet. So GRU is followed to capture the time information. We choose attention pooling instead of static pooling. Finally, branch of fully connected layer is used to the final classification. The loss function of the network is C cross-entropy loss. The output node of network is directly used for classification, and each node represents a different language. We build our system based on PyTorch. Both convolutional and recurrent operation are building blocks that persist one local neighborhood at a time. When faced with those long-range dependency, it is impossible to capture enough information to characterize the data. So the non-local block is used in the network to maintain more information. Some paper has shown that non-local block can achieve better performance when it's added to the early part of the network. So we add the non-local block at the top of the network. We use embedded session as the powers function to compute the similarity. The second subsystem we named is GCNet, GRU-net VLAD. The input of the network is still a 40-dimensional F-band. Compared with the first subsystem, the network structure has three changes. One is to replace the non-local block with GCNet. The other is to replace attention pooling to net VLAD. The third is to change the loss function into AM softmax. The output nodes of the network also represent different language and are directly classified. Then I will briefly introduce those three modified models. The first is GCNet, which is actually a simplified non-local block. GCNet fully combines the capability of non-local global contact modeling and can also reduce the amount of parameters and the difficulty of optimization. The second part is net VLAD. Net VLAD is improved from VLAD. The main innovation is to embed the traditional VLAD structure into the neural network structure. Net VLAD effectively aggressive the statistics of the first-order descendants of different clusters. Net VLAD enables the network to use feature more effectively. It improves the ability to extract the same categories and improve the ability to distinguish. The third part is AM softmax. Softmax mainly optimizes the differences between classes and is not good at reducing intra-class changes. AM softmax introduces angular merging into softmax, which can minimize intra-class variation and is more conducive to the aggregation of intra-class. AM softmax put forward stricter requirements for the correct classification. Visualizing the future distribution, it can be clearly seen that AM softmax is more conducive to cluster the intra-class. The above is the introduction of the two subsystems we designed. When training the network, we summarize several effective experimental settings. In one batch, we assure the example in languages were the same to ensure the data balance. For example, task 1 is identifying 6 languages, so we set the number of a batch size 6 multiplied 40. The second is the trunk size. The performance is better when the trunk size is larger with a certain range. We set the trunk size to 150 to 200. The performance is better. The third is the learning rate. When the loss between two epochs does not decrease, the learning rate is half. And the last one is the model fusion. We fuse the models obtained from different epochs as Caldi does. In order to ensure the matching of training data and the testing data length, we did score average. We cut the task speech into overlapping segments and send it to the network to obtain the score of each segment, and then calculate the average value of the final scores of the speech. Finally, we made a score fusion, extract back future of the past speech, do the VAD and the CMBN. The future was sent to the two subsystems respectively to obtain two scores, and use the weighted alpha and beta add the two scores to the final score. This is flowing our entire system. In fact, we have made some other attempts. The first attempt is to complete an end-to-end speech recognition by using the joint CTC attention. We have built an end-to-end speech recognition system, and the output of the framework is phonemes in all languages, and then get a language label based on the phonemes. However, the list of phonemes we can prepare is not so accurate, and the training data is not enough to train a robust end-to-end ASR system. The second attempt is based on the hypothesis that the differences between two different languages are mainly due to the combination and the distribution of phonemes. For example, Japanese volume frequencies is higher than Korean. So we pre-trained an acoustic model using THC-HS30 dataset, and then fine-tune the upper classification network using the target languages. We test this subsystem in the evaluation set. There's our experiment results. The pre-trained acoustic model and the joint CTC attention are not good enough. So we finally choose the end-to-end subsystem to submit the results. We use the answer provided by the organizer to find the best alpha and the beta. The best and alpha and the beta the best result we get is 0.0433 in task 1, and 0.0512 in task 3. And the final result we submit is followed. In task 1, the final C average we submit is 0.0477. Then in task 3, the C average we submit is 0.0538. That's all. Thank you.
Thank you very much, Dr. Yang. Can you hear me?
Yes.
Yeah. I think we still have several minutes to ask questions. I think this is a very good opportunity for audience to raise some questions. Anyone want to ask some questions? we have more than 90 attendees. If you have any question, just turn on your microphone and okay, Dr. Yang, can I ask a question about the overfitting problem? You know that especially in the cross-channel task, I heard some complaints that the website and the value side seems quite different, and they found that the parameters or models chosen by using the DOM site is not quite suitable for evaluation. Have you seen the same problem, or how did you do to solve the problem?
Yes, it is very clear that can you see us the PPT? First, we found that the overfitting problem is mainly because of the data mismatch. We found last year the audio provided by the task set is clear that some has mainly don't know how to say that. Like the presentation shows, it's been compressed. Yes, it's been compressed. So we first compress the data in order because of the I think the language recognition is just like the speaker recognition. The channel information always influence the final result. So the match between the data and the training and the testing is very important. So we change the data format in order to get the we want to get as same as the testing. So we do the convert. So we do the data preparation work, and as can be seen in our final results, the results we submit is not the best we can get, mainly because of the mismatch problem.
Okay. Thank you very much. If your audience have more questions, you can ask your contact with the speaker, with Dr. Yang, afterwards. And thank you, Dr. Yang, again, and a very good job and very good presentation. So, okay, so we move to the next presentation. Let's see. The next presentation is from Royal Flash, and can you hear me, Royal Flash?
Yeah.
Okay, good, cool. I will stop my screen. Okay, you can go ahead. Thank you very much for the presentation, and congratulations again for your achievement.
Thank you very much, Professor. Can you hear me?
Yes, please.
Okay, let's go. Good afternoon, everyone. My name is Wang Ding. I'm from Helsinki Royal Flush AI Research Institute, and I'm very pleased to be here to introduce our task-2 system for this challenge. My presentation will include these 4 parts. The first is our system descriptions of the task-2, and the second is about the data preparation. The third is to introduce our experimental settings and the results. And the last is to conclude our work. First, I will give descriptions on our system. This is our system's configuration. it is a multitask transformer-based model. First, we train a transformer-based joint CTC attention end-to-end ASR model. Then we use transfer learning on the above ASR model. We train an encoder with attention mechanism as IID model and use it to classify the 3 dialects. The training platform we use is ESPNet, and the computing resource are shown in this page. 4 2080 type for ASR training and 2 1080 for the LID model. Next is about our data preparation. The training data for ASR are 3 data sets as shown in this page. The AP16, the AP17, and the Tsinghua 30. We only use 6 of the 10 appointed languages by the challenge committee to train the ASR model. And we use some strategy of the data augmentation. Also, as shown in this page, the train set for dialect identification is AP19 OLR dialect. And the development set of this task is AP19 OLR DEV and test sets as just the same as the baseline paper. Now let me introduce our experiments. Our experiment settings are shown here. The acoustic feature for experiments is F1 plus pitch, and we use different layer number for the ASR and RID models. And the RID model is initialized by using the ASR model. And the parameters we use as settings are shown in this page. Our experimental results are shown in this table. For task 2, we found that the end-to-end system significantly outperforms the X-vector or I-vector systems. However, because the system scores are difficult to fuse, only the output of the end-to-end system is used for submission. And finally, I will enter the conclusions. By experiments, we obtained following findings. During the training of the transformer-based joint CTC attention end-to-end ASR, the encoder of model is found to be able to obtain highly discriminating features of dialects, and the strategy of transfer learning on pre-trained ASR model can markedly improve the performance and robustness of that dialect identification model. And that's all. Thank you for your listening. And this is the contact information of our team. If you have any questions, please contact us. Thank you again for your attention.
Thank you very much, Dr. Wang. Yeah, I saw a question. Did you try the score fusion of multiple subsystems from Zhengli?
We just try some X vector and I vector experiments on this task, and we found it is it performs just not as good as our end-to-end system, but the scores between these systems are difficult to fuse. But for the end-to-end system, due to the time, we don't have time to take many times experiments. So the submission the scores we submit is just one system, and we we started to have some experiments for this task recently, and we found that the fusion of these systems may be helpful, but you know, it's just too late.
Okay, you mean it's not so easy to fuse the end-to-end system with the other systems, right?
Yeah.
Okay, but you can just use skull fusion.
Just like this.
Right. I mean, in this case, it's quite the performance is quite different. So the end-to-end system, I think the performance is it's EER. I'm confused. So your end-to-end system is end-to-end system for ASR, right? And then you borrow part of the ASR model to retrain end-to-end system for LID. Is that correct?
Yeah, yeah.
Okay. Okay, so Zhang Li, do you have extra questions about this problem? About this confusion? Or maybe Zheng did not hear me. Okay. Rafael has a question. Why did you only use 6 languages for AS training? Why you did not use more languages, more data? Why?
The one reason is that some language in this 10 language pointed was difficult to pre-process, such as the Korean. So we don't use it. And the other reason is that this task is the dialects identification. So we use some we use the Cattons and the medium Chinese, so that we believe it would be very helpful for our system to learn the language features for this system. And the experiments show just the same as we expect.
Right, the hypothesis is fine, but did you use any experiments to justify the hypothesis? Because it's quite important. It's reasonable to say that if we use some similar languages to train model, and it'll be helpful for dialect detection. But another hypothesis is that if we have more data, because all the data from human beings, right, and we have a better, more robust model to for the next fine tuning. Did you do any experiments to test which hypothesis is correct?
I'm sorry we didn't take these experiments because during the experiments we only take the experiment that about 2 or 3 models. And recently we plan to you know, take a research of this, and all these 10 languages, I think if we use all of this, maybe it would be helpful for other tasks, but for this task, the experiment we had shows that this is the best result.
Okay. Anyway, you are planning to use more experiments to test the assumption, right?
Yes, yes.
Okay. From Miss Beach, how many output nodes in your ASR network? Probably the scale of the network.
About 100 and it just the number of the number of UTT is about 40K, and the hours of the data is about
Sorry, Dr. Wang. I think the question was the output nodes of the ASR network, because your network is end-to-end, right? And you
Yeah.
use multi languages. And what I think the question was, what are the output nodes, and in total, how many nodes are there when you train the end-to-end model?
About as shown in the page that we have
Are they lighters or some phones or?
we have about 6 nodes for ASR training and 3 nodes for LID training.
6 nodes. It seems quite strange, right? It's ASR network.
It's just yeah, you see the number of nodes of the network is the words the modeling unites
Exactly, output nodes.
about because we use word as the modeling unites, so it's about
You use the words.
I'd like to check my
A model unit word.
is 1024.
1024. Okay.
Maybe we should check our. It's a big number, right? It's we need to recheck our experiment settings, but the nodes of the network is just as the number of the words.
But you have you have 6 languages, right?
Yeah, and the words, and we built the model as using the modeling unites as the word, so it's a very large number.
Okay. This is I think the NDU, XDU, Yi Zhou Peng had the same question. What the stuff is, BPE or letter? What the? But you said it's worse, and it's a little bit strange, because using the small the limited training data, and you use such a big number of outputs, it's a bit difficult to train. But anyway, probably that you used some tricks. Okay, let's see if Yi Zhou Peng, is that your question, or do you have any additional questions for this stuff?
No, I just mean maybe the previous question, how many output nodes may mean the number of type states of the outputs of the end-to-end network?
Because it's end-to-end, so probably no type states.
Okay. Maybe the token number.
Right. Token number. And Dr. Wang said that it was words, the number of words, but then a little bit. Right. Anyway, I think the likely they had some tricks to do that. Okay. I think I have the last question because I know that Royal Flush had attended our challenge for at least 2 years, and you have achieved rather good performance in both the 2 or 3 years. I just want an idea that do you think the task design for this several years are appropriate for you to attend?
Some task is very interesting and full with challenge. So I think so. I think yes.
Do you think it's challenging enough?
Yeah.
Okay. I think after the workshop, we'll talk about our attendance of participants to discuss something about our task. Maybe we can revise our task and to meet the true request of academic or industrial partners. Okay, anyway, thank you for your great presentation and congratulations again
Thank you very much.
On the 3 tasks and not only this one, the task 1, task 2, right? Thank you very much. Okay, let's move to the next presentation. Dr. Wang, can you stop your share? Okay. So our next presentation is from NTU XTU, and yeah, lots of people, and I'm familiar with many of them. Congratulations to NTU XTU and thanks a lot for agreeing to present your details. Can you hear me?
Yes.
Perfect. I'll stop the screen. Okay, go ahead.
Good afternoon, Chair Wang Dong. Good afternoon, everyone. I'm Hai Hua. I'm from MICL, SE, Lion Technology University. Today, I'm on behalf of our team. Yeah, our intern from Xinjiang University, Zhang Jiten and Peng Yizhou. Yeah, for this work, I'm here as their supervisor. Okay, today we're going to present the following 3 items. First, we give a brief description of our task and data. Then we give a brief review our results, some part of our interesting results and analysis. Finally, we conclude and give our vision for our future work. Okay, as we know, first task description, as we know, there are 3 tracks for this year challenge. First is a cross-channel. To understand cross-channel, that means training data and test data are mismatched. How to solve this problem remains a big challenge for machine learning. Okay, for task 2, Chinese dialect identification. There are 3 dialects in this year. For task 3, noise language identification task. This is also very challenging to us. Okay, let's give a brief review of our data, organized data. The data can be defined in 3 parts: training, enrollment, and test and development. Okay, here the blue stands for the training. The orange stands for the enrollment data. And the green, the light green, represent the this year's new task, dialect recognition task. We can either use this data as a training or as a enrollment data. Okay, for the dark gray is Mandarin data. We can use whatever we can. Okay, we can treat it as extra out of domain or what in domain data to employ as much as possible data to boost our performance. Okay, for this year data definition, the main challenge is that for task 3, the organizer haven't specified the specific data set. That means training, enrollment, and the development. So it depends on each participant to define data. So based on this situation, so we define data from by ourselves. The motivation is this: number one, we want to make comparable results on cross-channel task in 2019, as cited in this bottom the bottom line of the reference. So we define enrollment data following the previous year. For task 2, because we want to fully explore, we want to explore the role of the new data. So we want to merge or want to solely use this part of data to train our classifier or the S extractor, okay, whatever end-to-end system. We want to see its performance on the development data that are defined by the organizer. So for task 3, it's obvious we have to define the data, okay, by ourselves. This is obvious. Okay, why should we define the data for the task 2? We just conduct experiments for this role, for the role marked with, maybe this is the green color, okay, not the green, okay. With this color, we first merge this part of new data with the previous training data. We got extremely bad results. This makes us guess that if the data is speaker overlapped or the data overlapped with the dev data that defined by the organizer. So we conduct first experiments. We solely use this new data as training data to train our X extractor. We still get better results as the last row indicated. So this is why we define the data. Okay. For task 3, we define data following the following principle. First, we identify overall noise data as well as clean data set. We found only Russian and Korean language are noise data. So this is not okay for a noise identification case. It's not enough. So we want to create more noise data for the remaining clean data. As a result, we treat Russian and Korean language as noise data and then inject it to the clean data, and hopefully we got the noise data for the other remaining languages such as Chinese, Cantonese, and Japanese. Okay. Finally, we define a remote data set with these 5 languages. The main principle we use is that we ensure there are low speak overlapping between enrollment data set. Okay, this is quite important. This is crucial. We found that one speaker, enrollment speaker and dev state speaker are overlapped. We can get extremely better results than the case that without speak overlapping. Okay. Now let's take a look at our data augmentation method. We conducted a series of data augmentation methods. Speed perturbation, quite conventional. Spec augmentation, that means we perform a spec augmentation on both the frequency axis and time axis. Okay, I think everybody knows about this technique, right? Number 3, we add in noise. Okay, also everybody participants knows about the rule. We cannot use out domain data. We cannot use data that are not released by the organizer. So we treat Korea and Russia as noise. Then we add Bible noise and music noise to the clean data. So here we see the result from this table. So sorry, let's go back. The first row shows that the baseline results. We use 5 epoch. We use Cordy S extractor. Okay, we do this. with this baseline, you can treat it. Then we use we use the speed perturbation and noise, both spec augmentation. So that means times 5. Okay, we got better results, right? After that, we try spec augmentation. We still got further significant improvements on performance. Finally, we found that from our ASR experience, we got the experience that for spec augmentation, we should try more epochs to iterate. Okay, so here we show that with 15 epochs, we got significant better results. Okay, this is our experience shared with our fellows. Okay, we also conduct data analysis on the task 1. Sorry, we found that quite weird. The dev data, the distribution of test data is quite narrow. The length range just between 2 and 3 seconds. Majority of the data, maybe over 90%, 95% of data, okay, the length about 2 and 3 seconds. And our training data is okay, it's widely distributed, is normal. So our test is quite singular. So how can we deal with this problem? Okay, we want to randomly chart, we want to cut our training data and let the data cut data in small piece and let length comparable to our test data. Okay, we randomly cut, and we conducted lots of experiments. Unfortunately, we haven't got any improved result with this kind of recipe. Yeah, so we still use the training data to deal with this case. Okay, for the classifier, okay, we want to see first this topic. We want to first see the data augmentation, the benefit of our classifier training. That means data augmentation can yield robust classifier. Okay, this is first this is the top table. Okay, as you can see, once we merge the speed perturbation and the speech and the noise injection method based data augmentation method, we can get significant performance as indicated last row of the table. Okay. For the classifier category, the organizer many thanks to the organizer. They provided a lot of classifier for us to choose, for us to test. Okay, we also conducted extensive experiments for the classifier category selection for this special for this challenge, because we are afraid that this data is low resource data to some extent. The other way, the data distribution is artificially manipulated, so it's not so natural. Okay, this is our only guess. So we conducted extensive experiments. As we can see the bottom 2 table, we just see for this simpler task, we show the logistic regression still outperformed the other method. Okay, so the whole experiment, we stick to use logistic regression as our classifier. Yeah. Finally, we use the same-thread learning on our task. That means pseudo-enable. Why? Maybe this previously in the early stage we are afraid. After to some extent we are afraid this maybe not comply. Maybe this not comply with the requirement from the organizer. So anyway, we want to try. Why? Number one, we are afraid the enrollment data and the enrollment and test data are inconsistent, are mismatched across channel. So we cannot guarantee that our system, that our classifier trained on the enrollment data that can be applicable, successfully applicable to our test data. So it is worthwhile to try, if we try to verify, okay, to do this, to solve the problem. So we think of pseudo label. We want to use the first recognized results, then according to some thresholding method to select data, then retrain our classifier to see if we can get better performance. Thankfully, we got a better performance. As we can see from the table, from this figure, as this figure indicated, with appropriate data selected, we can get significant performance improvement. Okay, let me explain. Number one, sufficient data enrollment is not enough. Number two, enrollment might be mismatch with the final test data. So this motivate us to do this some same-square training. Actually, pseudo label or same-square is quite popular in ASR area. So we apply this. Okay. Now, as everybody can understand this, think about this. What if your test data is quite a mismatch with your training data or your enrollment data? How can you guarantee your next label is eligible? Okay, this should be answered, right? How can we do this? How can we solve this problem? How can we release this concern? Okay, so our concern, our problem, our method, our approach to this problem is that we use this. We first recognize we use our initial recognizer classifier to classify our data, target data. Then we get the label, hypothetic label, right? We then use threat coding, select some part of data. Then in return, we test this on our training data. We want to see if it can get reasonable, acceptable results on our training data, right? This is very reasonable, right? This makes sense, right? Intuitively, this makes sense, right? So this is our motivation to conduct these experiments. As we can see, we can see that with about 60 or its range is quite wide. With about 50% of data selected, we can yield acceptable result on the training data. Okay, that means our pseudo label is working. Okay, number one. Number two, this decide how much hypothesis label should be selected for the retraining of our classifier. Okay. Conclude. Our efforts on the following three aspects. First, data analysis, redefinition. I think data is first, number one. Without data analysis or definition, we can make this because we found there's some mismatch. Okay, and data is quite a huge chunk. The previous year. Okay, data augmentation, augmentation, speed perturbation, intermittent noise as noise, intermittent noise as noise for noise injection. Number three, spectral augmentation is very effective. Now, okay, the final recipe, the final focus is the same-square training with pseudo label. We show it is working. Yeah. By the way, we haven't conducted a system compilation. We can, but okay, we do not. We think of this, but okay, we want to see how good our single system it is because this is more practical, right? For future work, okay. Right now, we are very interested in is we are ongoing also joint learning. That means, as we know, right? Language identification is pure classification. ASR is a sequential labeling, is sequential classification. Okay, but people usually study these two areas disjointly, separately. Is this true? Is this consistent with our human being? No, obviously no, right? Human can recognize can write speech content and simultaneously recognize what your language have said. This is obvious. So we can think of with prior pioneer work, literature work, we can do this in terms of the end-to-end or conventional DNA-HM system, right? Right now we already submitted paper for this in the archive. If you're interested, please contact with us. Okay, we use this. We just means we want to do this. We embed the language information into our word or phone level. Then when we do ASR recognition, we can also do language identification. The results are quite promising right now. Okay. For the multitask learning, this is very intuitive, right? We train a joint encoder. We then use two decoders to do language identification, and the ASR recognition is natural. As already shown in the from our previous presenter, Royal Flush. Okay, they already use ASR as initializer, ASR method to initialize their. So that means out of domain to initialize their encoder part. Then they use the classification, retrain it again. They can get, so as a result, they can get much better results. Okay, for the transfer and acceptor, this is very natural extension. Since for transfer learning, we can take advantage of for transfer learning, as already show our colleagues from Roy Flush. Okay, he actually uses some kind of transfer learning, first ASR, then that. Okay, it's not on. I don't think it only restricted for such for what Royal Flush has done. We can use a lot of domain data to train. Then we transfer to low resource case. Okay, we get hopefully we can get a better result. For summer training, this is also natural. We have a lot of unlabeled data. We have a lot of unlabeled data. How can we exploit sufficiently explore such unlabeled data? This is also very interesting for machine learning area, for SI area. We can get a decent results, right? So we also want to try this. Okay, that's all for my today's presentation. Thank you very much for your attention.
Thank you, Haihua.
Yeah,
Thank you for the presentation. I see some questions from Amit. The question is, could you please explain a bit more about the pseudo labels and what are the axes in figure page 12 to 13? Yeah, this is also my question. What are the pseudo labels?
Is this right?
12, is it 12?
No idea. Let's see.
5.
5?
No, sorry, 12.
12. Okay, 12.
12
okay,
13.
We do pseudo label like this. Okay, we first use our classifier trained on the enrollment data or the combined the overall training data. We then we first recognize our hypothesis data. That means either depth data or evaluation data. Then we use posterior score, right? Category class posterior score to select the label, the data with higher posterior. Then we merge with our data. We merge our enrollment data to create a classifier. Then recognize again. Then this is our method. This is very conventional, right?
To be honest, this is a little bit confusing to me.
Yeah. Okay.
Because it's okay if you use the development side, but if you use the evaluation side to perform the pseudo labeling, and then reuse the label to perform to retrain the model, I'm not quite sure, but we need to discuss more. It looks like not a usual way to.
Yes, I agree. For in this area, it's not usual, but for ASR, it's very natural. Use such kind of things. So that means we use a thresholding to select that. We first guarantee that our classifier is working on our given data. That means it should not get rubbish results. Then we select the data with higher posterior. That means this is very natural. That higher posterior means correlated with, that means your accuracy should be very high. So we select those labels, merge. Then that means we have some knowledge about test data. Yeah, this is not usual way for the speaker identification or language identification. I see. Yeah, I agree.
Okay. Any other question? We still have 1 or 2 minutes to ask Haihua. Okay, so about the in-domain noise injection, how you get the in-domain noise?
In-domain noise, okay. We do like this. We treat overall utterance as the noise data. Then we treat it as noise to add to our clean data. That means it's the Bible noise. But this Bible noise is quite special. They are noisy and they're background noise and or music noise, something like this. That means we first identify there are 2 data sets, right? Russia also I have mentioned. Korea and Russia.
I see.
both the-
Okay.
Yes.
We inject the noise data from Russia. Okay, I see.
Yes.
I saw you use something like VAD to cut the noise and then use the noise.
No. We haven't used VAD. We haven't used such a kind of method. For VAD, we only conduct these kind of experiments. We just means we want the utterance names comparable with our test data.
Okay, I see.
Yeah.
Okay.
Yes.
Okay.
Yes.
Thanks, Haihua. If you have
Okay.
any questions, yeah, you can just contact Haihua and the team for more details.
Thank you.
Congratulations again, and thank you very much for the presentation.
Thank you.
Okay, I saw some answers from Royal Flush. They gave some explanation about their end-to-end system. I think they can see the answer. I think they gave us a good explanation. So I think we should move to the next presentation. Let's see. Okay, our next presentation is from Phonexa. Okay, Phonexa, can you hear me?
Yes, thank you. Thank you for invitation.
Okay, thank you very much. All right, go ahead.
Thank you for invitation to this workshop. My name is Josef Slavicek, and I'm going to present the winning solution of task. So first, let me briefly introduce our team. So we are Phonexia. We are a company providing software for speaker ID, language ID, and tasks like this. And we are in the field for something more than 10 years. Maybe if you don't know the name Phonexia, there is another name which can be more familiar for you, and it's Beauty Speech Lab. People like Schwartz, Matejka, Borget, or Chernotsky. So if you know any one of them, you know Phonexia too, because we are started a spin-off of this lab, and these guys are owner of our company. So it was about us, and now about the task too. I believe we can skip this slide because we are all either participants or organizers, so we know what was the task too. It was about the dialects. So let's move to another slide, and finally our solution. So winning solutions of competitions like this are usually some fusions, sometimes huge fusions of many systems, but this time we won it with just one ResNet 18. So maybe it sounds exciting. Maybe you ask, did we found some magical way how to train ResNet 18 to solve LID problem? And the answer is no. Unfortunately, no. All we did, we took a fairly generic, simple training recipe. If any one of you will be asked to train ResNet for LID, you will do something similar, and you will get similar results, similar accuracy. And on top of this, we did two improvements. One of them was spectral augmentations. It was mentioned in the previous presentation, and for task 2, it shows to be very, very efficient. So it was one huge improvement. And the second one was training without mean normalization, which sounds crazy because we are using mean normalization all the way, starting from David Snyder X-vector recipe, and it always helps. But there was something specific on task 2 data, and turning mean normalization off helped a lot. We tried the same thing on task 1 and task 3, and it destroyed the results. So it was really something specific just for data of task 2. Here is table for results. So it's a relatively huge amount of numbers. So let's take sense of it. So here are two blocks of columns. It's def set and eval set, it's clear. In some rows, there are confidence intervals. We just trained the same setup 3 times and with different seed for neural network initialization. So this confidence intervals shows how much is the solution sensitive to random initialization of neural network. You can see surprisingly that for some setups the intervals are really wide. It's nice. And now let's go to individual rows. So first two rows of the table are baseline. They are provided by organizer. This is just copy pasted from the evaluation plan. The rest of the table are our results. First of all, you can see we trained on a little bit more data than was the baseline system. It's detailedly described here. And next, the individual systems. So this row is, let's say, our base systems. So mean normalization was here because we are using it all the way. And there was no spectral augmentation because it was based on old script where we didn't spectral augmentation. And with this system, we got very similar results to better of the baseline. So it was a nice starting point. And now to the improvements. First of them was the spectral augmentation. And you can see it helped a lot. There is not much need to say about what you see the numbers. And the second improvement was turning the mean normalization off. And you can see another big improvement, and that's it. The last row of the table, it's our final system used for submission. We just, it's exactly the same setup of the previous as the previous line. We just run the setup few times and we chose the best one of them. So it's about our result. And now let me restart the PowerPoint because when I use the marker, it becomes a little bit unstable. And we can continue. On the next 4 slides, there are, I hope, all the necessary information from anyone who would like to reproduce our results. It makes not much sense to go through it in detail, so I will stop only on some interesting on non-standard things. And first of them is the spectral augmentation. The vanilla original recipe for spectral augmentation it's just to take the input of your neural network, your features, and you are doing something like cutoff on it. And maybe you are doing time warping. Our approach is a little bit different. First, we are doing no time warping, so it's one thing. And the second one, we have a little bit more complex pipeline. We start from signal, we create a full spectrum, so we have some 256 spectral bands. And we are doing the masking on this spectrum. And from this, we convert back to the signal. So if you wish, you can listen to the utterance and you can hear how much is distorted and so on. And from this reconstructed signal, we are creating the features. So it's one thing. And second one, if you are using augmentations, you can use it to increase size of your dataset. But this was not the case. We just plug the augmentation as last part of our pipeline. So the amount of data remained the same. It was just another distortion applied to the dataset. So about features and files for neural net training, we used Kaldi software for data preparation, and we have a little bit non-standard script for creation of final files used for neural net training, but there is no magic about this. It's just to have a little bit more control about the data. So it's one thing you cannot replicate because you don't have a script for this, but the differences in the result accuracy will be negligible. So this was this. And about neural network, I told that we are using ResNet 18. In fact, it's smaller than standard ResNet 18 because we have the number of channels divided by 2. About statistic pooling, we are using the simplest one published by Snyder in X-Vector paper, so just concatenation of mean and standard deviation. Now here are hyperparameters for neural net training, so it makes no sense to read it here. And the last thing is backend. It's important thing, but very simple. We just take what organizer provide and use it. So it was just taken from the baseline systems. This our architecture. You can compare it with standard ResNet 18 and you will see that only difference is the number of channels, which is smaller. And it's all. To the conclusion, here is just repeated what I already told. So in some sense, we apologize to organizer because we didn't come with some new exciting solution, with some new breakthrough architecture. Task 2 of this competition was possible to win with just one ResNet, so we did it. That's all. Thank you for your attention. Thank you.
Thank you, Joseph. Any questions from our audience? I think it's quite interesting to see that the simple approach can output other more complex system combination or such. It's very interesting. Professor Hong asked the question: why not use VAD? Is there any special reason?
We tried to do it with VAD and without, and we got better results without VAD. So.
Well, this is a little bit strange, as well as the CMN and the CMVN, because usually we saw better performance when we apply the CMN CMVN, especially in our previous experiments. So is that the observation of just the task 2, or you find the same observation in other tasks?
I don't understand fully. I understand you are asking. So I mean, can you please repeat the question?
Yeah, no CMN and no CMVN. You find that the VAD and the CMN does not work, right, for your task 2. This, to me, this is a little bit strange.
Only for task 2. When we did it for tasks 1 or 3, there with CMN we got better results. So it was really something specific for task 2.
Okay, so it's just for task 2. All right, I see.
Yes.
So this is a little bit strange. Maybe the data dependency. Okay, other questions? Why no CM show better? Oh, yeah, this question is there any idea why the CMN shows better? No CMN shows better, at least
No.
on task 2?
No, we didn't much experiments because we had very limited time for this competition, just few days. So we just tried something, and by chance it worked, and we won it. But
Okay.
we don't know.
Yeah, I saw that after you apply the spec org and then you found the problem, you observe the phenomenon. So I'm curious, if you don't apply the spec augmentation, and if the conclusion will be the same or different.
Without
Wait.
spectral augmentation, the turning off CMN will still help. The conclusion will be the same.
Okay,
It was not caused by spectral augmentation. It was something independent.
I see. Okay. Okay. All right. Another question is from Wang Bingling. Is you prepared the EGS on Kali and trained them on PyTorch. How did you achieve that? How did you prepare the EGS on Kali and train them on PyTorch?
There is some recipe on GitHub. Author is Hossein Zainali, and he did it. So we just took this, and our approach is based on this. So on GitHub it can be found. Maybe if you will contact us by email, which
okay, right,
which is on the first page, we can send you a link to the GitHub repo.
Okay. Any other questions from our audience? All right. So if no, we thanks again to Joseph for the presentation, and congratulations again for the winning. Thank you very much.
Thank you.
All right. Let's move to our final presentation. Yeah, our final presentation is from L'Oreal in-real multi-speech team, and yeah, Rafael MD in-real and Dennis. Can you hear me?
Yes, hello, can you hear me?
Yeah, good. Rafael, okay.
Hello.
Yeah.
Can you see my screen?
Yeah. Good. I will. Yeah. Yes. It's clear. Go ahead.
Okay, thank you. So I'm Raphael Durzel from team L'Oreal in-real multi-speech, and I'm very happy to present our work. We are a team of 4 people: Mohamed Saïdoula, Irina Ilina, Denis Jouvin, and myself, from a French lab called L'Oreal. First, I would like to thank the organizers of the challenge. It was a good opportunity to test our hypothesis about language recognition systems development. The main focus of our work is language recognition on unknown condition for domain mismatch. So we mainly focused on task 1, and we also submitted our system to task 3 since we thought that noisy language identification could be addressed with domain robustness technique. So here is the outline of this talk. First, I will present a global strategy to address this challenge, and then describe the 3 main components of our system: frame-level features, language recognition model training, and the final SCORM fusion and calibration. So our goal was to design a robust system for unknown conditions, so specifically task 1 and also task 3. The constraints of the challenge are that we can only use the 16 languages provided in the training corpora, and that recordings from unknown channels that is the goal of task 1, are only provided for 6 languages coming from task 2 of the evaluation 2019. We call these 6 languages development languages, and they are different from the languages of task 1 and task 3. Also, transcriptions are available for 10 languages that can be used to train automatic speech recognition models. And finally, it was forbidden to use any other corpus, which can be a problem for data augmentation techniques. So based on this goal and these constraints, we divided our work into 3 sets of experiments. First, we wanted to train bottleneck features, since we know that they are state-of-the-art language recognition features. For this step, we used all available recordings with transcriptions. It corresponds to 10 languages. And then the question was, how do we use that recordings from unknown channels? There are mainly 2 ideas. Either we keep them for testing to evaluate the robustness of our system to unknown conditions. Either we include part of the data into the training set to increase the diversity of the set and hopefully to improve generalization performance of our model. So these 2 ideas correspond to 2 steps of our experiments. In the second step, called optimization for system robustness, we only train model with mobile channel recordings, and then we are able to test on really unknown channels. And for once a robust recipe has been selected with these experiments, we train systems with a bigger training set, including data coming from unknown channels. So here are the data sets used for each set of experiments. For each set of experiments, we define a training and validation set and several test sets for the 2 last steps of experiments. The difference between optimization for system robustness experiments and final system experiments is the use of the data coming from task 2 of last year's challenge. It is only kept for testing in optimization for system robustness experiments, and it's partly used for training in final system design experiments. All this data can be used with data augmentation techniques that are known to improve performance, especially for deep neural network training. We designed 4 strategies that abide by the rule of the challenge of not using any other data set. So first, the addition of synthetic white noise with different SNRs, the addition of bubble noise that was created with other files of the training corpora, the processing of our recording with bandpass filters of random in order to simulate unknown channels, and finally spec augment that correspond to time and frequency masking. So next, the first step of our experiments was to select frame level features. We explored 2 kinds of features, spectral features and bottleneck features. So for spectral features, we compared male filter bank features, male frequency capsular coefficient, and shifted delta coefficient based on MFCCs. For all frame level features, we applied speech activity detection based on the implementation of CALD. These features were compared to bottleneck features that are state-of-the-art language recognition features. Usually, bottleneck features are extracted from a neural network that is trained to predict for each frame a target phone or triphone. These phone labels come from a forced alignment between frame level features and transcription. And for this forced alignment, we need an automatic speech recognition model. For this challenge, we did not have the time resources to develop an automatic speech recognition model for each of these 10 target languages. So instead, we decided to only train 1 multilingual automatic speech recognition model based on an end-to-end architecture with 1 output layer for each target language. So we define tokens with a sentence piece model for each of the 10 target languages, and we trained the automatic speech recognition model with an end-to-end loss, so the connection is temporal classification loss. And basically, we select this model, the best automatic speech recognition model, on the CTC loss on the validation set. What we observed is that model regularization is a key aspect of this training, and that we improved a lot generalization of the speech recognition model with spectral mean and variance normalization and data augmentation. So basically, we train this model and we extract frame level features from a hidden layer of the network. So then we use the domain robustness datasets that correspond to only training on mobile phone channels, and we test on 3 test sets. Test 2018 that only contain mobile phone channel, and Test 2019 and Test 2019 that contain unknown channels recording. And we only train a TDNN with 4 different kinds of feature and variable performance. So we observe that bottleneck feature trained with our recipe are better than spectral feature for all test sets, and that bottleneck features extracted from a model trained with the regularization techniques are better for language recognition on 2 of the 3 test sets, and especially the most challenging one, Dev 2019. So we selected these features for training of our language recognition models. The next step of training is to train the language recognition models. So we use 2 kinds of models, deep neural networks based on the TDNN architecture and Gaussian mixture model. For the time delay neural network architecture, we used the standard architecture, and we did not use any backend, but used the system predictive score. It was trained with the 16 languages of the training set with stochastic gradient descent with dropouts. One interesting point is stochastic weight averaging that was mentioned by one other team. Instead of selecting the model with the best validation loss, we averaged model parameters along the trajectory of the gradient descent, and it improved generalization. So this TDNN was trained with the baseline cross-entropy loss, and then to improve generalization to unknown conditions, we trained it with other loss functions with 2 different ideas. First, replacing the cross-entropy loss with a state-of-the-art classification loss function. So we use the additive angular margin softmax loss function, and then adding a regularization loss to the cross-entropy loss that enforces invariance between known and unknown channels for activations of the network. Regularization loss is added with a weight parameter lambda, and we tried 2 different loss functions, maximum mean discrepancy, which is a domain invariance loss function, and n-pair loss, which is a metric learning loss function. And then we also train Gaussian mixture models for language recognition that we found competitive to TDNNs, especially for short utterances. So we trained language-dependent Gaussian mixture models with SDC MFCC input features. We used 4096 major components, and it was trained with the well-known expectation maximization algorithm. So then once language recognition models have been trained to achieve the best performance, we have to calibrate scores and to merge predictions of models. So these 2 steps were performed in the same step with the focal toolkit with a multi-class logistic regression for the 16 languages of the trained corpus, and then we extracted log likelihood ratio for languages of task 1 and task 3. So why do we need to merge scores of several systems? It's because systems are complementary. So here is a comparison of 4 systems for task 1 for our 2 test sets, test 2018 that correspond to known channels and test 2019 that correspond to unknown channels. So we basically compare 4 systems, the Gaussian mixture models, our best TDNN trained with additive angular margin loss function, the fusion of both models, and our final submission, which is the fusion of these 2 models with 3 other TDNN. So basically, we observe that for known conditions, our best individual model is the mixture model, so it corresponds to the left plot, the black curves. And that the fusion with the TDNN trained with additive angular margin improves over this performance, and that fusion with 3 other models does not improve further. Conversely, on the right plot, we see that the TDNN trained with additive angular margin is a lot better than the Gaussian mixture model for unknown channels. That fusion of both is at full, correspond to the red curves, and that by adding 3 other systems that were trained with domain robustness loss function, we improve further. So to achieve the best generalization performance, we need to add more models to our score fusion. So here are the scores on our test sets of our final models. So we have 3 test sets, the test set 2018 and 19 corresponding to known and unknown channels, corresponding to dead curves of the previous slide, and the validation set that correspond to the same condition as the training set. There is one system, one TDNN trained with cross entropy, 4 other TDNN trained with other loss functions, so the TDNN trained with additive angular margin loss function, the TDNN trained with n pair loss, and 2 TDNN trained with maximum mean discrepancy with different value of the maximum mean discrepancy loss, 1 and 100. And finally, there is the Gaussian mixture model. And our submission is the fusion of the last 5 models, so 4 TDNN and 1 Gaussian mixture model. So what we observe is that for each test set, a different model achieves the best performance. So here the performance is C average. So on the validation data set that closely matches the condition of the training set, the best recipe is the standard training of a TDNN with cross entropy. The generalization to non-channels, the better system is the Gaussian mixture models. It corresponds to the test 2018 test set. And the generalization to unknown channel corresponding to test 2019, it corresponds to the system TDNN trained with additive angular margin loss function. And the 3 other TDNNs do not achieve the best performance, but were trained with the objective of reducing domain mismatch. And that what we can observe is that the gap between performance on test 2018 and test 2019 is really reduced in comparison with other models. And we think that it can explain why they are useful for generalization to the unknown conditions. And finally, as was mentioned in another presentation, we have no information about the duration distribution of the test set. And in addition, the distribution of duration of our development sets was quite reduced. So what we decided to have a more secure system was to learn the calibration parameter for 3 different ranges of duration, so corresponding to duration inferior to 2 seconds, between 2 and 4 seconds, and more than 4 seconds. So here is a description of our final submitted system. So we use 2 kinds of spectral features, male filter bank feature and SDC MFCCs. For the TDNNs, we use multilingual botanic feature extracted for an automatic speech recognition end-to-end model. We have 4 TDNNs trained with different loss functions and 1 Gaussian mixture model. We extract scores from these 5 models and we perform a duration-dependent fusion and calibration and extract log likelihood ratio. The same system was submitted to both task 1 and task 3, and we did not submit a system to task 2 since we do not have experience with dialect identification. So here are our final performance on the test sets. So we are quite happy of this result because they closely match the performance on our development sets, validating our data engineering strategy. So here are conclusions from this work and from this talk. Our main idea was to combine two strategies: evaluating robustness on unknown conditions and using diversity of data in the training set to improve robustness. We confirmed a previous result, like the importance of data augmentation techniques for training neural networks, both for automatic speech recognition and for language recognition. We extract botanic feature from an end-to-end multilingual automatic speech recognition model, and it seems to work for language recognition. Modeling found that Gaussian mixture models were competitive with TDNN for this task. We observed that different loss functions are complementary and that system fusion is crucial to achieve the best generalization performance under known conditions. And also, we found that the trick of stochastic weight averaging during gradient descent improved generalization to the test set. Thank you.
Thank you very much, Raphael. Let's see, any questions from our audience? Right. Jingli gave a question. Could you give more details about extracting a Babel noise?
Okay, yes. So we filtered with KLD energy-based VAD all recording from the training corpus, and then for a recording, we randomly selected a few other files from the training corpus, so between 3 and 7 other files, and corresponding to other languages different from the recording we want to add noise to. And we basically cut the sampled 3 or 7 other files in small chunks and added them to the files we want to augment with different SNRs, and the range of SNRs corresponds to the KLD augmentation recipe. So I think it's with SNR between 5 and 20, but I have to check.
Okay, right. Another question is, did you compare the performance of GMM and iVector because they are both generative models? And the question, iVector or iVector?
No, we did not use iVector except the baseline system that was provided by the organizer. So we did not use iVector at all. And this work needs to be performed.
Okay. See, any questions? Right, I have a question about the duration-dependent calibration. So, what do you find the real contribution of the duration-dependent calibration? How much is the contribution?
So the contribution is not that important. Since you provided us labels from the test sets a few days ago, we were able to evaluate performance of this part, and so it's slightly improved from about 10% relative improvement for task 1, our performance, and for task 3, it did not improve at all. And we have to check by looking at what I think is that we need to have longer files in our calibration data set to achieve a better performance on the test sets of the evaluation.
Yeah, I agree. Yeah, our test sites are almost in the same length, so it's not easy to get improvement. But for the calibration, you mean to tune the weight for different systems or tune each individual system?
know to tune the weight for each system because basically the 4 TDNNs were trained with various durations, so ranging from 1 to 5 seconds duration of segments. So we hope them to be quite robust to a mismatch in duration. And the last technique is just to find the optimal combination of system for each range of duration.
Okay. Right. The final question is, I understand that you pay much attention on the robustness of the system, and you try to use some individual development site rather than training the model with all the data when you develop the system, develop the recipe, and but finally you still combine all the systems together. I just want to know, you have paid much effort on the robustness of each system, and then when you combine them, is there any impact at the final stage? I mean, at the fusion stage to reduce the robustness? Did you find that?
That the fusion of several systems reduce robustness to unknown conditions because some systems are less robust than others. Is that what you mean?
Yeah, right.
Yes, I am not sure. We do not have precise results to understand it. We are sure that it's a risk, but at some point we had to define a test set to evaluate robustness. So we kept some of the unknown conditions to the test that we call test 2019, and since we managed to improve performance on this test set, we selected this model. Our idea was to limit the number of final models that we merge. Maybe we could improve a little further on this test set with other models, but then it would mean overfitting the calibration set. So we decided to stop and to only add the Gaussian mixture model that is complementary to deep neural network and for neural networks, but trained with losses that are known to be robust losses for domain mismatch. So that was our strategy, but it was not controlled since we did not have data from the real unknown conditions.
Okay. All right. Well, I think there is another question, the final question. Why the GMM system, the old technology, shows as good as the TDN system? Do you have some conjecture?
Why the Gaussian mixture models are as good as TDNN?
Right.
No, we do not have conjecture. It's work we are currently exploring right now. Maybe it comes from the features because this Gaussian mixture model was trained with SDC MFCC, comparison with the TDNNs that were trained with multilingual botanic features that come from male filter bank features. Maybe it comes from the features because when the Gaussian mixture model is trained with our botanic feature, performance is not as good because maybe because the SDC has not the same meaning for botanic features that from MFCC. So it's our hypothesis right now, but we are exploring it and we have no conclusion for the moment.
Okay, thank you very much. Thank you, Raphael, for the presentation and for the answering the questions. And congratulations again for the winning. Right.
Thank you.
Let's move to the next part. Okay. This time we are very pleased to invite the Professor Hydro Lee to give us to share his view about the language recognition. As you know, Hydro is very active in language recognition. I remember the first paper I read for language recognition is from Hydro, and he worked on SVM-based approach, worked on the language model-based approach and many innovations. And Hydro is very famous on all the fields of speech processing. I don't think I need to introduce more about Professor Hydro Lee, and we thanks a lot to Hydro to share you will. Hydro, you are there?
Yes, I'm here. Can you hear me?
Okay, good. Yes.
Okay.
Okay, I see you, Peter.
Yeah.
Okay.
I can share the screen. Can I? Yes.
Sure, yeah.
Okay. Do you see the full screen? Yes, right.
Yes.
Yes. Okay. Good. So thank Prof. Dong for the invitation, and I congratulate the successful organization of the evaluation OLR, and I'm just now I saw the participants, the number of participants. We have 80 over people in this workshop. This is in my view is the largest gathering of language recognition studies in the recent years. So OLR actually represents the largest community efforts as of today. Just now, I got the chance this afternoon to have some other events, but I managed to attend join some of the sessions. I'm impressed by the results by the several groups, and particularly the last group, Laurea Lab. Actually, it was the laboratory where I spent my postdoc research in France. So I'm very glad to see my old labs continues the research in speech processing. I also joined the very beginning. At the beginning, Prof. Wang talked about where language recognition should go. I think this is a topic that in our mind, everybody's mind for a long time. Today, I would like to share with you a few slides. It's not a comprehensive study, but I do have some thought in the past years, and I would like to take this opportunity to trigger some discussion. This is like a picture of many directions, and we are like at this place and deciding where to go. So let's look at the realities. I feel that the language recognition research in the recent years actually is reduced. The effort is reduced very much. If you look at the numbers, NIST, the last evaluation was 2017, and it did not organize further. And of course, speaker recognition, there are many more. It's like has the momentum. The momentum continues. If you look at the papers in ICASP and interspeech, I happen to be the area chairs sometimes in those conferences. You can see I counted the past few years. Typically, it's like 5-1. There are 5 papers in speaker recognition, and there's only 1 in language recognition. And I feel that this is a very sad statistics, and the community may want to brainstorm to reverse the trend. And later on, we may discuss what are the reasons and what can we do. I also find that OLR, my team actually participated in several evaluation, and we follow the NIST LRE formulation, which is good. And but I feel that as we are now represent the largest group in the speech community, perhaps we may innovate to lead new directions. We can discuss what are the topics, and we may formulate a new evaluation schemes to lead new directions. So I cited a paper that I wrote in 2013. That time that was before deep learning came to mainstream, and but since then I do not see a deep learning approach making a systematic approach of deep learning approach to language recognition. So I think that could be the topic that we can explore. We always talk about channel, speakers, domains, and mismatch for language recognition, and I think that this continue to be the directions. But there are a few areas that I think that we may want to look at. I remember that in 2010, NIST proposed evaluation called human-assisted speaker recognition. Basically, the idea was to understand how humans do in terms of speaker recognition in comparison machines. So today we have many, for example, our accent recognition. We have organized many rounds of evaluations, and the error rate was still rather high, between 20 to 30% of equal error rate. So there was a discussion on actually how humans perform in those tasks, whether machine has already done better than humans. So this could be a question, and also from there, perhaps we can learn what human use as the cues to differentiate the languages. And the second topic, the second point that I list here is we know that there are many work in speaker embeddings in speaker recognition. There are many papers. Actually, half of the speaker recognition papers are focused on speaker embeddings. But I do not see many papers working on language embeddings. Language embeddings in the sense that we build embeddings for different tasks. For example, we build language embedding to do voice conversion, to do cross-lingual synthesis, or to detect switch of languages in the sentence. There are many use of it, but I do not see too many research in this area. And now we have a lot of, the third point is now that we have a lot of data, and know that the BERT GPT models in language models is pre-trained model, and people use very much in respective applications. And I feel that language ID could be something like that, because language is not related to speakers. It is, and the world has only a fixed number of languages. Actually, the number is reducing. So there could be initiative that in these areas, and that is related to database speech resources development. Then there are also in speaker recognition, we see many evaluations moving towards audiovisual language recognition. That could be an area. And the last thing is we have many, we most of the time when we evaluate systems, we kind of evaluate the equal error rates, we as a result we kind of stay with safe engineering methods, and that kind of innovation is neglected. So maybe we can kind of organize a prize that is given to best innovations in evaluation, so that we can diversify the techniques and we can promote novel contributions. And another trend of the evals in the last few years in different evaluation campaigns was moving towards applications. So I think what are the applications for language recognition? Speaker recognition, there's a voice print, the voice biometrics, and it's kind of one big directions. And where are the applications of language recognitions? So actually, there are many applications that are waiting for our technologies. For example, when people who work on multilingual speech recognition, you know that we need to detect the change of languages. So if you analogy to speaker diarization, then it's called language diarization. That works for code switch speech recognition applications. And there are also other areas of multilingual speech recognition that may need language cues. I always think that we don't use a speech recognition system to detect the language. The language should come from an independent model. So when you do speech recognition, you have acoustic model, language model, then you may have a third model that is modeling the language, and this way you can handle code switch speech recognition very well. So how our techniques can be used in the downstream applications, and these are actually reflected in the similar thinkings are reflected in other evaluations. I say that we prepare these slides and learn from others. So in speaker recognition, actually in the last few years, they moved towards applications very much. For example, there are tasks of multi-speaker tracks. That means multiple people talking to in the speech, and they want to recognize the target speaker. And there are also audio-visual tracks in the latest evaluation. For voice conversion challenge, they include cross-lingual conversion, and actually they need language embeddings in their evaluations. So and anti-spoofing evaluation, they actually work with voice conversion communities. So one is kind of a synthesizer voice, another try to detect a synthetic voice. So I see many partnerships between the evaluation campaigns to address application needs. In particular, for the anti-spoofing evaluation, they actually incorporate the task into the downstream automatic speaker verification applications. So to evaluate the performance of the whole system with anti-spoofing front end. It attracts many participation as well. Lastly, I noticed that there are some major efforts in the community working on multilingual speech corpus development. These are two papers that I recently came across. One is an effort that's called Common Voice, which claims to be the largest open source multilingual speech databases. It has collected contribution from 50,000 individuals. So basically, there's an app that you can download, and then people from different countries, you can record your voice, you can contribute to the database. And more than 2,500 hours of collected audios are already available. And maybe our initiative can leverage on some of these databases. For example, if we are talking about pre-trained language embedding, then this database can be very useful. And another one is called VoxLingua. This is a database that is collected automatically from internet, basically YouTube, the audio of YouTube. They use a software to crawl languages, spoken languages from YouTube channels. And now they also have collected 6,000 hours of speech, and some of them are verified, cross-verified by the community. So I feel that maybe some of our tasks can, if you want to venture into like open domain training, we open up the training to be to allow people to use open source data. Then this could be good source of databases to use. We grow one pair of ears to listen, and I think that these are the language resources to grow the ears for language recognition. Then we can focus more on the language specific aspects of study. So that's all I have to share with the audience, and I take some questions. And I know that many researchers my friends are in the audience. Yeah, please give some critics to what I talk about.
Thank you very much, Professor Lee. Any questions? I think this is a very good opportunity to talk the leading scientists in our field.
How do I unshare that?
I think one suggestion is really good. Innovation award. I think this is quite interesting, right? Because new technology is not necessary to win others at the beginning. We should award the innovative ideas rather than just winning of the competition.
Right. So I think set criteria to say we will have a selection of algorithms and innovative ideas, and we can pick one that kind of encourage people to think creatively rather than stick to the safe methods. Yeah.
Right. Yeah, this is a very big issue. Yeah. Any other Professor Hong is asking, do you think ASR can be combined with LID for the multilingual ASR? I mean, add new task for multilingual ASR, Professor Lee.
Right. So this is a good question. So yes. So I'm always thinking that the development of our language ID technology should one day be adopted in a big way in applications. Just now I mentioned speaker recognition, easy to explain. You have voice print, to verify a person's identity. But for language recognition, we need to find this, and I find that multilingual ASR is a perfect application. So we have many. Actually, there are several code switch databases available, publicly available, and so far I do not see many applications where people use LID to improve the code switch speech recognition. So I think that's a good idea. Of course, if we want to go for this evaluation, somebody need to prepare the data, and then there's effort involved.
Okay. I think due to the time reason, we will not ask more questions. Thanks to Professor Lee for the interesting supervision. I think this is quite inspiring, and we will talk offline later what OLR should be refined. Okay. Thanks a lot, Professor Lee. Okay. Now, can I invite the our sorry, let's let me share my screen again. Okay, can I invite our organization team and Professor Lee and the winning team to turn on your camera and we have a picture together. Okay. Ms. Yang Cheng, can you see us? Okay, Cheng, please take a picture. Okay, I saw many faces. Welcome. Okay, cool. All right, Cheng, if you have finished the photo taking, just let me know. Okay, I think it's okay. All right, thank you very much.
Okay.
Okay, yes, it's fine. All right.
Thank you.
Okay, thank you very much. I think we are towards the end. And I just want to take the opportunity to thank all our participants and all our presentations. And they are very interesting in technology. And especially, I'd like to thank Professor Haizhou Li to give our new directions and very valuable suggestions. I think it's a very good supervision for our future work. And an announcement is that we have tried to organize a special session on InterSpeech 2021 next year. We have proposed the proposal, but I'm not quite sure if it will be accepted. But if it will be accepted, we will send the message across our friends. If you have papers, please submit. And last one is the OLR next year will be announced soon. Before that, we may send out some questionnaires and ask your opinion, what the major direction and what your suggestion. And we will also take the suggestions from Haizhou Li and other professionals to enrich our challenge. Finally, thanks to Liming from Yang Cheng from Speech Ocean, and you work very hard to make the workshop successful. Okay, thank you very much. And any comments from our organization team? Liming?
I'm good, Professor Wang. I'm good now. Yeah, thank you you for everybody joining us. Yeah.
Okay, Professor Liming. Okay, fine. Sally?
Oh, okay, yeah.
Yeah, I'm fine. Thank you for your attention.
Yeah, thanks for taking the role for the moderator. Thank you.
Okay, so we end. Thank you very much. Bye-bye.
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 Bye-bye.